Now this model is closely connected with simple harmonic motion. Very simple way. Okay, R of t is a vector. If we have radius A, constant angular velocity omega, then wherever r is at a given time, this vector has an x component, the I component. So what we have here is x of t equals a cosine of omega t times the I vector. So that the x-coordinate of this point is just a cosine of omega t. Now we recognize that as an equation for simple harmonic motion. Okay, simple harmonic motion, which when t equals 0 corresponds to a vector from here to here. Your r vector would be here, so the x component is the whole vector. So the x component is a. Now, as you move around here, the x component becomes 0. As you move around here, the x component becomes negative a. So you have motion from a to negative a and back. And of course, omega, or t keeps increasing. You keep going around the circle and around the circle, so you have an oscillation from this point back to this point to this point. So right there is the connection. And we say that simple harmonic motion is just the projection of a point moving around a circle of appropriate radius, the radius being the amplitude, at the appropriate angular velocity omega, which we know for simple harmonic motion to be the square root of k over m. And let me remind you, I want you to know how to derive that. I want you to know why it's a square root of k over m in terms of Newton's second law, and a little bit of simple calculus. Okay? Simple, but for some reason, not all that easy to always remember. So you want to make sure you do understand that. Keep reminding yourself. Okay, well, we also have a vector here, y of t is a sine of omega t times j. So we have this. And this is again an equation of simple harmonic motion. In other words, the y-coordinate being where the tip of this vector is just an a sine of omega t, which we know from the derivation of this and all the stuff we did with simple harmonic motion, which we know then is the other solution to the equation mx double prime equals negative kx. And maybe I'll write a little reminder here. Premise that you have a linear restoring force, and that force is the net force, m times acceleration, mass times acceleration, or mx double prime. You really want to lock this in completely. Okay, so there we have it, the connection. So as this point moves around, the x-coordinate does this, and if you start here, t equals 0, the y-coordinate starts here, goes up, comes back down, all the way down to here and back to here. Starts at 0 and goes through a simple harmonic motion, going up to a positive displacement, back to 0, down to a negative displacement, back to 0. Cosine starts with a positive displacement here, goes to 0, max negative displacement, back to 0, back to the maximum positive displacement A. Okay? So, big connection. We call this the circular model of simple harmonic motion. Something I want you to carry with you throughout the course. Now, that's one important set of relationships for circular motion. Okay, another really important relationship, and there are at least a few of them, is the orbital motion of a satellite around a planet, okay, or the orbital motion of two planets about their common center of mass. Okay, and we haven't characterized that completely, but we do need to know something about circular motion in order to do that. And that's the next thing I want to look at. The application, the circular, see there, started right at U, orbits. Not be more specific of that. You'd have, well, you generally wouldn't have a circular orbit around a two-planet system, although you could. But there'd be some perturbations. Maybe there wouldn't. Anyhow, we'll work it out.